you can go ahead and get
Oh,
started.
sounds good. All right. So today I have Professor Ermin Wei with me. How are you doing today, Professor?
Doing well. How are you?
I'm doing great. Good to have you. Now, Professor Ermin Wei is a professor of electrical and computer engineering at McCormick School of Engineering, right?
hmm
That's
And also industrial engineering and management sciences.
sounds good. Yeah. Good to have you today.
Yeah, thanks for having me.
Sounds good. So usually I have this meeting in person, but as you all know, we're dealing with a pandemic right now. So there's a
Right.
lot of social distancing going on. So we need to do this over telecom, which I'm sure everyone is okay with, right?
Yeah, yeah, it's fun. I mean, I get to show up my cool virtual background here.
That's good. That's good. Now, to start us off today, Professor, can you give us a summary of your journey through science? So I'm interested to know what sparked your interest in the sciences and how that led to where you are today as a professor at a prestigious university.
And how far back would you want me to go? Like from childhood or starting from college?
We can start from maybe your undergrad.
Sure. Okay. Yeah. Okay. So that's actually an interesting story. So I finished all my 10th grade education in China.
Hmm,
And then when I was in my 12th grade, due to some family reason, we moved over to the US.
hmm,
Okay, so at that point, then I started applying for college and needed to decide on a major. So since I was little, my parents they are both mechanical engineers. My dad's a professor.
hmm,
Um, so they were always able to fix whatever breaks in the household and design cool machines. I always knew I wanted to be an engineer because that's like the most useful thing that I know how to be. And I always loved science and math when I was growing up. So then, so why did I mention the Chinese background part? So I wanted initially to be a doctor, like an actual doctor, not a PhD doctor,
hmm,
and a biomedical engineer would be the closest one. But since I learned all the biology in Chinese and chemistry, the mapping from Chinese over to English was really, really hard. It's not
hmm,
just English, it's also to Latin and
hmm,
other languages that the bio part are stemmed from. So
hmm,
at that point, I decided I should do something that I can handle. So I was interested in engineering, and I did not want to be. Well, I could not be a biomedical. And then also, my parents said we already have two mechanical engineers in the house, so we don't need another one. So that was out as well. So it kind of started to being a pretty small set to choose from. But I'm really, really glad I did what I did, which was I was the computer engineering in my undergraduate because for one, the computer programming has always been English, so there was no language barrier. It was pretty easy for me to transition through. Two is I really like these animes and cartoons like Transformer, that type with robots and artificial intelligence, really, really smart, helping the world, saving the world.
hmm,
So I wanted to be part of that program, and so that kind of inspired me to become one who's interested in math and engineering, so the combination in between. And then so I started off as a computer engineer, and then I started doing undergraduate research there. um, I was in a robotics lab, not too surprisingly given my
yeah,
interest.
naturally.
Yeah. So robotics turns out to be a lot of control theory, and that is turns out to be a lot of math. So my research advisor told me, why don't you take 1, 2, 3, 4 math classes? And I looked at the curriculum. If I take 8 math classes, I can get another degree in math. So so I just went down that path and took a bunch of math classes and realized I really, really enjoyed doing the more rigorous part of the curriculum. So, like in calculus and all those more introductory math classes, they give you a tool and you can go ahead and apply it and do something with it. That was super cool stuff.
Mhm,
But as I took more and more advanced math classes, we were not developing more tools, but rather try to understand what's behind all these tools. How did we get to the point where we can use these tools? Where do they come from? And turns out even a very simple statement has a very deep story behind it, and it kind of goes all the way back to the axioms of math and different branches. So it kind of opened up my worldview on mathematics. And that, kind of guided me through, I want to pursue deeper studies. So I went and did a PhD. And then now I'm further and further away from transformers, from the robotic side. But now I'm doing things related to the transformers on the electricity side. So I guess
where did you do your grad school and your PhD?
I went to MIT. So I did my undergraduate at the University of Maryland, College Park, where I studied computer engineering, mathematics, and finance. And then I went to MIT to do my PhD, and then I joined Northwestern right afterwards.
Okay, so you did your postdoc at Northwestern?
I did not do a postdoc. I went directly from a graduate student to a faculty.
So it seems to me you've actually always wanted to be a teacher then, after maybe a few years in school, maybe 2 years in school, you figured, okay, at this point, why not go into faculty,
At some point in my undergraduate, I wanted to build a startup, building these robots, household robots that can be helpful for, doing laundries. I think that was my first robot that I wanted to build.
Okay. I mean, it's never too late. And if anything...
I don't know how long you want me to spend on this topic. I have a few anecdotes I can tell you.
Save that for later, right?
Yeah, so sure.
We can finish up with that, okay?
Sure.
So on your school profile, it says you're working on large-scale distributed algorithms, right?
Mm-hmm.
And theory with emphasis on nonlinear convex optimization, right? So what is that in a nutshell? That's a mouthful, obviously.
Right. Yeah. So maybe I can start telling you how useful optimization is, right? So everything.
So I have a feeling we're going to talk a lot about algorithms today, right?
Right. Yeah.
So, well, it seems like the idea of algorithms itself is as old as mathematics, right? So the ancients used algorithms to solve early math problems as mundane as division and even finding prime numbers, right? So fun fact, right? So the word algorithm itself comes from a 19th century Persian mathematician. So his name was Muhammad ibn Musa al-Khwarizmi, right? So to you, what's an algorithm, Professor? What's the definition of an algorithm?
Okay, an algorithm, well, it takes an input, does something to the input and spits out an output that solves whatever the problem is. So to me, it's kind of like a function. It's mathematical mapping from input to output.
Right. Hey, that's very good. I mean, that's very digestible for anyone who's listening.
Yeah, so optimization or distributed optimization. So let me parse it, right? So optimization is essentially, you have a task you're deciding when you eventually can go outside your house or where you want to go, which route to take to their destination, for instance. That's something to optimize over, maybe to minimize the travel distance, maybe to maximize your exposure to the lake view or other things, right? So as soon as we start talking about minimizing, maximizing, we're talking about optimization. So it has some kind of goal in mind, right? If you're planning production, you want to minimize cost. If you're planning economy, you want to maximize social welfare. So all of these and day-to-day work, we are naturally doing optimization. So the distributed part, so I'm thinking about the large data area where there's a lot of information to be processed. So it's not like just planning, a commute route, but something slightly more larger scale. Then we might not be able to do all the computation on one computer, especially in this big data area with deep neural networks and complicated models. So yeah, as a result, we might want to have multiple computers running things in parallel. And how do you distribute the computation task among these different processors, so that they can collectively still recover the global optimal solution as if they are one single computer, but they can do things in parallel. So get the speed up, but not sacrifice the quality of the solution.
All right, awesome. That's pretty good. So before we go any further into the meat and potatoes, right? I'd say let's set the stage with the more rudimentary terms and ideas, right? So I'd want us to maybe touch on Lagrangians, right? So
Okay.
in physics, it's a more, I guess, sophisticated way of calculating mechanics, right? So unlike Newtonian or even quantum physics, right, it doesn't really give us any sort of new, concepts, right? Now, how do we use Lagrangians in algorithms?
Okay, so I mean, for me, I mostly think about Lagrangian as a duality tool.
Okay.
So and in calculus, it's related to the slope, the tangent line next to the curve. It's a very geometric concept. The
That's right.
first time I learned about Lagrangian.
Hmm.
Now that from the optimization point of view,
Hmm.
duality, it's a little hard to explain.
Hmm.
I guess abstractly, it so instead of so you have something to optimize,
Yeah.
right? So that's let's say you have f of x, or they have an x, you're trying to find the minimal solution. So you're trying to go down as the algorithm goes more, it evolves more to recover the global minimizer. Now the Lagrangian duality kind of offers you a alternative way. It flips into another space, and you can try to maximize in the alternative space. So the picture I would have in mind is you have one space you're trying to go down to the minimal solution, and another space you're trying to go up towards the maximizer. And when the two meets, then you are at the optimal solution. So it kind of helps to give you another dimension to work with in some sense.
Okay.
Yeah.
So I'd say at the heart of algorithms is computational complexity theory. So we
Mm-hmm.
use that to, I guess, sequester algorithms in relation to the level of complexity, right? So is it safe to say that the complexity of an algorithm is really related to the amount of, I guess, time or energy spent to actually calculate that algorithm? Yeah.
Okay, that is a great question. Okay,
Okay.
conventionally, if I just have one computer, normally they look at the runtime complexity,
That's right.
right? How long it takes.
Hmm.
So in the distributed setting, these notions are slightly different.
Sure.
Okay, and this is something that my group is evolving to define this, and we're still debating on what is the right thing to do. So you actually mentioned the two of the very important one.
Mm. Oh, 1 second. I think we lost audio.
Oh,
Oh, it's back. It's back now.
oh, okay.
Whoa.
Yeah. Do you repeat any parts?
1 second. Let me see. Um, where you started from, what your lab is working on in
Yeah,
regards to
we are defining what is the right notion for to measure complexity or performance of algorithm for the distributed setting.
it? Hmm.
Okay, so you mentioned two great ones. One is energy, one is time.
Yes.
Right. So think about different applications, and I'm going to come back to my beloved robotic examples.
Yeah.
You
Yeah.
have a
I
bunch of
love robotics
robots.
too. Yeah. I mean, there's something, there's an affinity for robots and human beings. Although there's this idea of what the uncanny valley effect, right? So when we see automata or anything that has human sort of gestures, we kind of, I don't know what it is. It's a visceral reaction to it, and it's like, oh, okay, is that a human being? But we know it's not a human being, but our mind is like playing tricks on us. But I guess I looked into it, and there's actually a name for it, the uncanny valley effect.
Oh,
And yeah, it was. I think it was coined by a Japanese roboticist, Yashinori Moto, something like that, but I can't remember his name. But it's
uh-huh.
it's there. It's not your, it's not a fake idea, but it actually happens to all of us.
Yeah. Oh, cool. Good to know.
Yeah.
Yeah. So, so if I have a team of robots I'm deploying out to the field to do certain tasks, right? Then they would have to move around, and they probably will not be attached to a power cord the whole time.
Mm.
So and it may be okay for them to take their time to finish the task, as long as they can finish the task without having to come back and charge and redo it, which may take forever. So there the emphasis is less about time, but rather on the maybe energy constraint. right? Or if you have another case of processing high-speed computers that's all somehow connected by fiber, or maybe even shared memory.
Sure.
So there, the computation doesn't really matter, but rather the time is what matters overall. That's your measure. Oh, sorry, I meant the energy doesn't matter because they are, in data center, for instance,
That's right.
connected. We
Yeah.
have power outlet there, but the time is what's of concern. And
Yeah.
then the robotic one, so in addition to time and energy, so these are the two things that potentially are important. There's also memory access in the data center, and that may be a constraint. And in the robotic one, for instance, maybe it's not the time the algorithm takes, but how far your robot have to move around to collect the data. So there's also locomotion. So all of these somehow have to be captured by a measure of the distributed algorithm. And also, so I just mentioned a bunch of different settings, right? And you can tell by different settings, the standard or the measurements of what is a good algorithm should be different. So this is the notion that we're still trying to define properly, how to have a unifying measure of what a good algorithm is. And the best we can come up with is it's a metric depending on the application.
Okay, so it's undeterministic then, and that's what we want from our algorithms to begin with, right? So it's not a one size fits all sort of
Right,
situation.
exactly. You want some customizability. Depending
Yeah.
on the application, you can change your algorithm adaptively. So that's the kind of method that we are developing in our group here. Yeah.
Okay. All right, sounds good. So let's I guess take it even back a notch, right? So we spoke about complexity and determinism. So time and space complexity, right? So at a higher level, we're dealing with non-deterministic polynomial, time, NP. Actually, how about we touch on that? So the idea of NP, NP complete, NP hard. So for the uninitiated, what are those terms, and how does that apply to their everyday lives, would you say?
So okay, so P is generally representing any algorithm that you can find the answer within polynomial time, and it's typically a size. The polynomial function is the parameter is the size of the problem.
Sure.
And the NP problems would be if you ask me whether something is yes or no question, I can tell you the answer. Not within polynomial time, so exponential, double exponential, or anything that's more than polynomial time. So in daily life, I mean, generally I guess the computer scientists will tell you the line is between polynomial and non-polynomial, but as far as daily life is concerned, exponential is something grows really, really fast. Or I guess mathematicians say they blow up quickly.
Well, yeah,
So
we're dealing with a pandemic right now, so that's a good example, right, of exponential growth. So if
exactly, yeah, exactly. So that growth is
exponential, yeah.
exponential, and the reason why it's exponential is it's also something that we're working on. It's related to the network size. So you can view every person as a node in a certain graph, and you are connected to a few other nodes, meaning people in the same household or people you come into contact with, and then with certain probability. As soon as you come into contact with someone else, if you have the disease, it may spread to the next person, and it kind of goes along the graph, and that growth is exponential. Yeah.
So I think it's funny you actually mentioned that you guys are actually working on, I guess, helping the efforts, right? This international effort of combating the virus. So what's very, heartening for me is the fact that science just feels like it's at a standstill right now, and everyone is putting their chips together to, solve this problem. So for everyone else, it's just, okay, I'm at home, I'm, just following, the guidelines on how to social distance. But for scientists, it's like a I feel this is our sort of Manhattan project, you know. It's yeah, it's all hands on deck.
Without the secrecy.
Without the secrecy, exactly. Yeah.
Yeah.
So what are you guys doing in your lab when it comes to this, the efforts to combat the virus?
Right.
If you
So
don't
we
mind
are.
talking about it.
Yeah, no, I mean we're just getting started here, and we are not the frontline workers
For sure.
who
Sure.
have the capability to build the vaccine. But what we are doing is trying to collect some data and try to model the spread of the disease and to see. Um, so there are a few models. Some of them fits the spread pretty well already. There are a bunch of papers on those out. And so what we're trying to do is to see where we can efficiently test the potential patients and to try to stop the spread efficiently, because you might have heard in the news there are highly constrained supply on the PPEs and the testing kit, and all these resources are now very constrained. So we want to use them carefully and efficiently to try to stop the spread or protect as many people as we can. Yeah, so we're still just getting started on collecting the data and trying to analyze the scenario.
Awesome. So it's more on the logistics side of things, right?
Right. Yeah. No, we're not doing anything medical.
I mean, no, it's hey, every effort counts. You
Yeah,
know,
exactly. Yeah, but if we can figure out, for instance, who the PPE should go to and who you should test, right? So it may not be the people you usually suspect. Like
yes.
if the immediate neighbor of those who have come into contact, maybe it's more efficient to test the people 2 hops away, or maybe it's efficient to find the one who's more central to the network and try to quarantine that person and just try to cut down the network connectivity. That may help with stop the spread of the virus as well.
Wow, that's interesting. And I think computer scientists are kind of carrying their weight during this time as well. So I almost check the Johns Hopkins map almost every day, and just yeah, it's actually I think it's marvelous, right? That kind of technology, and it would just work seamlessly. But yeah, let's get back to algorithms, I guess.
Okay, sure.
So another concept I think is actually pertinent to our conversation today is convex optimization, right?
Okay.
So that's when we try to minimize convex functions over a convex set.
Correct.
Yeah. So how does that play into the work you're doing?
So so were you asking why convex, or so okay, I guess I'll start there, and you
Sure.
can let me
Yeah.
know if you're asking something else. So
Yeah.
convex optimization traditionally is like the baby step towards more general optimization. Why
Okay,
we
so
call it baby.
we do want to start from there then, right? Because it's actually
Exactly.
yes, awesome.
So it is a foundation to more complicated optimization, because the convex shape essentially means it has one local minima, which is the global minima. So it the curve kind of looks like a parabola,
like a cup
pointing
or a bowl.
Yep. So if we can solve that, then we can go into more complicated non-convex settings where instead of looking for global optimal solution, we will be looking at local optimalities. And so from the jump from convex to general problems is, I guess, easy to get in intuitively, but obviously from the algorithmic point of view, there's a lot of work to do. But the thing is, if we cannot even solve the baby step part, then we cannot do the more complicated case easily. Okay, so that's why we're sticking with the convex part. So you mentioned both the convex objective and the convex constraints. So the convex constraints are generally any nice constraint. Like, if you have a bunch of linear constraints, you get a convex constraint. And if you have something looking like this, ellipsoid constraint, you get a convex constraint. So that's generally pretty mild, unless you're dealing with power flow problems or communication problems and this very structured problems. So for now, by the empirical loss minimization problem from machine learning.
Mm.
So there, essentially you have a bunch of input output. You're trying to build a model that can fit the data mapping from are either unconstrained or constrained over a box constraint. So a nice convex constraint.
Okay.
Does that answer your question?
Yeah, I think so. Because if I was to, I guess, get a more holistic view of everything, right?
Mm.
So it seems like we're trying to solve data limitation issues, right? That are, governed by the fact of locality. So, right. So an agent has access to information contained in, I guess, some real world domain, right?
Mm.
And the whole idea is to how do we access that information, right? Is that correct?
So you mean the distributed setting?
That's right. Yes.
Okay, so it's locality, but in a slightly different spin.
Mm,
So locality means, so think about maybe large scale sensor system. You have sensors sitting at different locations collecting data,
mm-hmm,
and collectively the data should be combined into one global model that
mm,
fits all the sensor nodes.
sure.
But
Sure.
each of them would only have access to partial information. So
Mm,
that's the locality that we're talking about. You only know what your local data look like. And also the distributed setting means you have a limited communication. So meaning each sensor would be connected to a few neighboring ones, maybe the closest one within certain radius or
mm,
ones with line of sight, depending on the communication mechanism.
okay.
So with that, you have essentially access to local objective function, meaning the data collected locally, and also can only talk to a few neighbors nearby. So you each of the node cannot aggregate what the global function, objective function looks like, but it has enough local information to communicate through the communication and computation. You can recover the
Okay.
system-wide optimality.
All right. So what applications do you think would be recognizable to the listeners that these sort of problems are being solved in, would you say?
Yeah, so I think the sensor network one is a good one.
Yeah.
It can be any kind of information. For instance, if I'm trying to predict, I don't know, the amount of electricity consumption as a function of weather.
Mm,
So I just have a bunch of sensors out there
mm,
collecting temperature information and the local, maybe your smart meter collecting your local consumption. But I don't care about the average household, but rather on aggregate level.
mm.
I mean, I don't care about any particular household, but rather the aggregate representative average household. So there I would be, ideally, I would need to aggregate all the data into one location and then try to fit a model of temperature to electricity consumption. But
Sounds good. Sounds good. Actually, I'd want us to come back and talk about electricity consumption
okay,
later on. Yes, so that's very important. And again, I think that's one of those problems that everyone can sort of
relate to.
relate to. Exactly. So, by the way, what are primal dual optimization algorithms?
Okay, so
Yeah,
this kind of relates back to our discussion about the Lagrangian function,
exactly.
right? So by going through the Lagrangian function, essentially we can open up this space of the dual space, which I mean, for the audience who knows about Fourier transformation, there's kind of duality view of the time and frequency space. If not, anyways, it's just the two different dimensions. In one, we can go down, trying to go through the minimizer, and the other dimension, we try to go up, and we aim to have the two meet somewhere in the middle. That would be the optimal solution.
Mm,
So the primal dual method, the primal is the one where assuming the original problem is the minimization. The primal direction is trying to go down to the minimal solution. The dual direction is trying to go up. So primal dual method takes one step in the primal and one step in the dual and try to help the convergence. So it should get a little bit more speed up over regular, just only in the primal or only in the dual space.
oh, awesome, awesome. So I'd say it's time for a sort of intermission, right?
Okay.
So so on a more no, we're not going anywhere.
Okay.
We're gonna put down a bit of science, and so on a more congratulatory note, I guess you and a team of researchers at McCormick were top 10 finalists in the Department of Energy competition, right? That
Yeah.
was set out to maximize energy distribution, security, and efficiency. So, do you want to sort of talk about that competition and how you guys got second place and I guess bagged like $400,000? That's awesome.
I know it sounds like a lot, but there were five faculties on there.
I
And
know, I know.
anyways, so the money is not very important, but it
Exactly.
was a very much fun competition to be part of.
Mm,
So as you already mentioned, this is organized by the Department of Energy and
mm,
in particular the UPRE branch. So
mhm.
the goal is to come up with an algorithm that can solve what's called a security constrained ACOPF optimal power flow problem. So let's see. So background that would be coming from the electricity system, right? So we don't really think much about it. We plug in a phone, assume it'll charge it, and we flip a switch, the light turns on. So all of these are part of this interconnected electricity system.
Mm,
And on the system level, let me just try to talk the high level ideas. Is we have a bunch of generators that needs to be scheduled on how much they need to generate for the next 24 hours or whatever period you have as for your planning purposes. And then the demand realizes, and you try to match the supply and demand. So that's what's called the optimal power flow. So that's a power flow problem. The optimal part says we want to minimize the cost of generation. So if we have efficient generators, we try to use them. And all of this is running on AC flow, so it's up to ACOPF. And then
interesting.
the security constraint you mentioned, which is a unique feature of this problem formulation, is to account for potential failures of generators or lines. And these are also known as the N-1 problem. So you only have one generator or one line fails at a time. So you can plan assuming the best case scenario, but realistically, and certain lines may fail. There may be, a wind knocks down a tree that breaks a line, or maybe a generator goes down or has to be go into maintenance. So how do you plan ahead of time with these considerations in mind? So build certain robustness into the planned solution so that in case something goes wrong, you can respond quickly. So that's what the competition problem is. How do you with all these considerations, what kind of algorithm do you write? You can find the best solution for that.
Awesome. So staying on the issue of energy use and optimization. So I
Mhm.
read one of your papers and this idea or the concept of general sensitivity analysis
Mhm.
approach.
Yeah.
So what is that and how does that affect the lives of the listeners?
Right. So I guess I should probably start with demand response. I
Okay.
think
Yeah. So that
that would
basically
be a
what that gives consumers the opportunity to balance the demand and supply of I think energy by responding to certain time constraints, right? Time
right.
and
So
price constraints.
yeah,
Yeah.
yeah, that's the gist of it. So in some sense, when I get my electricity bill, it
Yes.
usually says, here's your consumption multiplied by unit price, and here's how much you owe me. And I go ahead and pay ComEd.
Okay.
But what ComEd pays for the generator is a price that actually changes every 5 minutes,
Hmm.
depending on the time of the day. And also it's different depending on where you sit on the network. So
Okay.
if you happen to be close to a nuclear plant, then at 2 a.m. in the middle of night, most likely your locational marginal price, known as LMP, the actual price the retailers, the wholesale market uh, transaction is based on, would be something negative.
Hmm.
Okay, and then so that's a wholesale market. Then what we pay is the retail market price. We
Sure.
never get to see those negative prices. At least I've never seen a negative bill that ComEd sending me.
Yeah.
So what we see is what's averaged over time and over lots of different locations. Okay, so this demand response concept, part of it is to say, what if we pass on these negative prices to the end user, so that, you know, if I have flexibility, I might do my laundry or do my dishwashing at 2 a.m. to utilize the negative price. So the reason why I mentioned the being next to nuclear plant is the nuclear plant is at a constant output level. Once you build it, it has to, you know, output at a certain level. It cannot change its shape following demand. And when people are at work and needs electricity, nuclear plant is still outputting at the same level as people are sleeping and not consuming much. So therefore, the prices can be negative to encourage people to use the electricity at that hour. So if we can pass that price on to the end consumer, then we can encourage the demand to help follow the supply rather than the conventional view of having supply follow demand. And there we might be able to use less of the conventional non-renewable generator to satisfy the demand, but get more demand to realize the potential to change its shape and also encourage renewable integration there.
All right, awesome. So another term that stood out for me in your paper is this idea of a prosumer, right? So this is an individual that consumes and likewise produces energy, right?
Yep.
So this sounds like something we should all aspire to be a prosumer. So how can we actually be prosumers?
Yeah, so prosumer, if you're in California, then I forgot the number. I think like 20 or 30% of households now has access to either solar rooftop or be involved in EV charging. And there it's very easy to be a prosumer. So essentially, well, consumer everyone can be by consuming energy. So prosumer, the pro part comes from producer. So you would need to be able to output back to the grid. So one way, if you are in the location with a lot of sun exposures, to put up a solar rooftop panel and to harvest the solar energy. Alternative way is to have a EV or some kind of Tesla power bank or battery that you can hook up to the grid. And when grid is in need, such as during the day or hot summer days where all the ACs are running, you can sell the stored energy or produced energy back to the grid.
All right, sounds good. So now the idea of demand response, right? It sounds like a noble effort, right? But what are the mechanisms in place that's hindering us to actually have this full scale, would you say?
Well, okay. So even though I was just saying my bill is never negative, but I am getting some signals from ComEd. So this holds for people in the Chicago area and in the ComEd serviced area. So hot summer days, in the morning, ComEd will send me a text message saying, today is going to be peak hour. We're going to reimburse you if you shed your load or reduce your consumption compared to your normal consumption. And if you do that, if you say normally if I cool my AC down to 75 degrees, if I see that, maybe I'll only cool it up to 78 degrees or something. So if I just do that, then I will get a rebate from the utility company. Okay. So that's the extent of things are as far as demand response is concerned. But as I said, their price actually changes every 5 minutes, and I get that text message maybe 4 times a year, and that's for the whole day. So I don't. Well, okay. One thing is I'm not going to sit here and change my consumption pattern every 5 minutes, right?
All right.
So I need so this is something that we as the field is working on to get more smart appliances that has automatic control that can utilize this potential and to not require human intervention in picture. Okay. So that's one thing, the missing of these smart appliances, but we're working on that. The second part is, I guess, the lack of incentive for people to participate, right? So for me, during spring and fall, the electricity consumption is like $20-$30 a month.
Yes.
So if I have to sit here every 5 minutes to tune a knob, maybe I'll pay, $2 less amount. And is it really worth my effort doing that? Probably not.
Mhm.
So that's actually an interesting question. This human behavior, or more a behavior related question, rather than the from mathematical point of view, we can say assuming everyone will maximize their payoff or try to minimize the amount they pay for utility company. But realistically, the amount is so small, it's really hard to incentivize every household to participate.
Yeah, it sounds like there's a lot of behavioral economics behind
Yep.
these theories, right?
Yep.
So
Yeah.
we want to maybe invest more in the prosumers that have the biggest impact on the grid, and I guess incentivize them.
Yeah, so that's what that paper is about, the one about general sensitivity analysis.
Right.
So the
I think
goal there is
I was just trying to repeat what you said.
yeah.
Yeah,
So we had the same question. We actually have a follow-up work that's looking at more the behavioral question with the data.
interesting.
I'll tell you about that later. But so the question that motivated this paper that you were mentioning is to say we have a limited resource on how to incentivize people to participate. So which household or which maybe manufacturer should we target? How do we know which one, if we can incentivize them to participate, which one would have the biggest impact on the social welfare? So that's what this paper is about. And turns out the tool to analyze this is the dual variable. So coming back to the optimization background. So in order to identify the most impactful prosumer, you need to find the one in some sense has the largest dual variable
Interesting.
associated with its constraint. Yeah.
All right. So another thing I found just fascinating was the market model you guys came up with, right? So that contained the prosumer that's trying to, I guess, maximize resources in one way or another, a utility company trying to maximize profits, and what is it, a distributed system operator, right?
DSO, yeah.
Yeah, is that the term? Yeah, trying to maximize the welfare state. So the DSO, right? Is
Yeah.
that like a local government? Is that a state? Is that a federal government sort of entity that's trying to maximize the social welfare?
Yeah, the distribution system operator, we are modeling that after ISO, independent system operator, that is in existence, not completely made up, and its
Mm.
sole purpose is there to balance the supply and demand side to make sure we have a reliable operating system.
Is
So
that
it's
a
not
government
exactly
sort of
government.
thing? Okay, it's not.
It's like a neutral third party entity.
Uh,
Its job is to oversee the operation of the electricity market and make sure things operate there in a reliable fashion. So it's not too far-fetched to say its purpose is try to maximize the social welfare.
mm,
Except for them, they have a slightly more weights on the reliability rather than the social welfare.
okay.
Yeah.
All right. So, what are the ideas behind, maximizing this utility, right? So how can we get more prosumers? How can we get the DSOs to, I guess, act in more fair, bipartisan ways? How can we have the utility companies not, because I think it's almost visceral, right? We have this sort of apprehension, or we don't really like our energy providers. I don't know about you, but I really don't like mine. Is it just the fact that they take money from us? But how can we, I guess, find some sort of stasis in the system?
So it used to be the utility companies are monopoly. Now, as they start to deregulate the electricity market, at least I'm starting to see a lot of mails coming in advertising, say if you switch to a different utility company, they give you, I don't know, Hilton points or something.
Okay.
So we are seeing more competition in the space of utility firms, and as more competition appears,
generally economists will tell you the more competition there is, the more efficient the market will be. So that would be one way. And I mean, I guess I have to speak for ComEd a little bit because we do, work with them every once in a while. They are working to install smart meters at different households, and so potentially in the future they can give you more closer to real-time pricing or kind of price signals, and they can collect data and know when things are going out, when their service is going out, without dispatching people to look around to see what's happening there. So they are trying. Some different areas have different ways of running, and just California utility companies are somewhat more innovative partly because they have a lot of more EV and solar rooftops to deal with. So they have to be more proactive in looking at these renewable integrations.
Okay. Yeah. All right. So can we talk about their grid system? So the fact that there are a lot more households that have solar panels, and are they starting to reap the benefits of this new innovative way of storing and utilizing energy?
Yeah, so that's can be a really, really long conversation. So they California kept changing the way they pay the households with rooftop, the solar rooftop panels. I think they are already on 4.0, so they kept changing different versions, and different generations have different payment schemes. So they are experimenting. I guess that's the short answer. Because solar rooftop is something, once you put it up there, once you install and hook up everything, it costs very little to produce additional energy. The marginal cost of production is close to zero, except you have to maintain it and make sure it's operational. So with that, initially, a couple of years ago, they were giving a lot of subsidy to people to incentivize people to put up the rooftop. And then they have to pay you to use the electricity you produce, right? So if you have one on your rooftop, you can produce and sell it back to the grid. So if you get paid to put it up, and every time you produce, you are getting paid again, then essentially it's not going to be a very good business model for the utility. So now they are changing that into you get the price they are paying you is going to be different, and also when you can sell back to the grid. So they are trying to learn what is the right way to do. One, to also make sure the utility company is still profitable and can stay alive. Two is also, it's not really good if everything is going on at the same time, if everyone's outputting at the same time, especially if it's not the time the grid needs the supply, the additional supply from the solar.
Okay.
Yeah, and also solar adds a lot of uncertainty into planning, because it's not something you can command to say at 12:30 I want this much solar output. So it actually makes the planning and operation a lot harder for them as well.
Okay. Sounds good. I'd say maybe we can bring back your I guess your foray into startups with your robotic company. Yeah, I'm actually interested to hear that.
All right. So I spent my undergraduate, did 4 years of research assistant in a robotics lab, and in the beginning I really thought I could build a robot that can fold your laundry, do your laundry, which shouldn't be that hard. Okay, I guess the story is like undergrad, the dorm that I was in did not have a laundry machine. We have to carry the laundry to a different building, so it's always a hassle for us.
Always a hassle, yeah.
Yeah, so that's why I kept mentioning laundry.
It's the pain point you had, and you were trying to solve it. In my opinion, those are the best companies, right?
Yeah, and those are the great engineer opportunities, right? So here's the thing, though. So in my undergrad experiment, we were doing echolocation localization. So I was flying bats and trying to study how they do echolocation, implement their algorithm onto robots. So it's a lot of fun projects.
Oh yeah, that does sound fun.
Yeah, so all of this should point to I'm now a CEO somewhere, right? So why am I not? Why am I a faculty here?
Hey, you
So
took the noble route. You're teaching the next generation of.
yeah, maybe one of my students can do it. So we were doing this localization indoor. So we have an indoor GPS system we set up in the lab that sends beacon into the robot, and the robot triangulate uses the signal you receive from a bunch of different sensors to try to decide where it is inside the lab and then moves around. Okay. So that's all great. Except during the demo every year, we have to move to another building, which is a fancy new building across the street from where our lab is, and set it up over there. And that's when we, talk to the potential prospective students, high school students, and try to attract current students to the lab. So every time we cross the street, something fails on the robot. So it could be something like, the hardware, the screw came off loose, we lost Wi-Fi. The computer needs a reboot, we lost Wi-Fi. Something fails, we lost control. So initially we were doing wireless control, and then we learned our lesson, we had a joystick. And so we have to do this like 3 or 4 times a year. And as far as I can remember, maybe every time except one, something fails and the robot would be stuck in the middle of the road. And that crossing is, in the middle of the street, there would be like 10 cars piled behind us and try to wait for us to reboot.
That's funny.
Yeah, so I'm great with math. I can write down the formula to triangulate and know where the robot is and write down the filtering, etc. But this hardware implementation, make sure your demo can go smoothly, or even just to be able to set up the demo to cross the street. Just so many things can go wrong. Exactly. And so at that point, I decided I want to stay with the environment that I can control, which is more on the theoretical side, and I can make nice assumptions and work out the theory, and let someone who's more skilled to deal with the hardware part. Because with me, it's always bad luck.
I don't know. I won't say it's bad luck. You know what they say about hardware? It's hard, right?
Yeah, right.
Let's call it hardware. So yeah, on that note of levity, I'd say we can wrap it up, Professor.
Sure.
All right. I really appreciate your time today. So now, if anyone's hearing this and they want to join your lab and they want to find you, how can they get in touch with you?
They can always just email me. So ermin.wei@northwestern.edu, or knock on my door. Except after pandemic's over.
Oh yeah, the pandemic. Yeah, it's put a real damper in everyone's plans, right?
Yeah,
So
I think emailing me is the best.
Yeah. Are you guys able to go on campus to do any sort of work or no?
No, I'm not essential worker. I don't have any live animal in my lab, so.
Well, maybe you should get some bats like you used to have. I think nowadays bats have this very bad rep. So I'd say maybe after the pandemic, give it like a year or two.
Yeah, now is not a good time to have bats around.
Going around with bats, all right?
Yeah, right.
All right. Well, on that note, Professor, thank you.
Yeah, it was a lot of fun. Thank you for having me.
No problem. Yeah, perfect. That was great.
Great, cool.
Thank you.